Okay, so this is going to be the final lecture given by Alexander or myself in the course. And every year this lecture is my absolute favorite one to give because it changes every year and it highlights kind of what are the latest and greatest advances in the new frontiers of deep learning and AI, while also complementing that with discussion about what are some of the limitations that we should be mindful of when working with and developing this technology. So before we get into the really fun stuff, we're going to just do a little bit of housekeeping, exciting housekeeping, starting with the fact that we have a long-standing tradition of course t-shirts in this class, and all of you all, for your participation and being here, are going to be able to receive a t-shirt. We're going to plan to deliver them and hand them out tomorrow after the end of the class, so please be here in person to receive your t-shirt. Okay, so kind of where we are standing right now in terms of the schedule and where we are at. After this lecture, tomorrow we're going to have 2 awesome and really exciting guest lectures. More on that in a little bit. And then on Friday, we're going to be really focused on the final project pitch, presentations, and competition. And so with the lab sessions today and tomorrow, hopefully you will have time, you will have incubated your ideas for the final projects a little bit, and are welcome to come discuss with Alexander and I, discuss with other course instructors, and get feedback on your ideas. There are also a couple of upcoming deadlines with respect to signing up to be in the list for the project proposals, as well as submitting your slides for the project proposals on Friday. A little bit more on that too. So you all have been working on these 2 software labs with respect to the music generation lab and the computer vision facial detection lab. The deadline to submit those labs, your entries for entry into the lab competitions, is tomorrow night. The complete instructions, details on how to do that are on the labs themselves, as well as on the course syllabus. We've received a lot of questions about the final project presentations and also what is required to get credit for the class if you signed up for credit. So going to talk about that a little bit. The first option for receiving credit is the proposal presentations. And these are going to occur on Friday. And the concept here is we're going to have kind of a Shark Tank style pitch competition for your ideas about new deep learning research projects, ventures, anything of that sort that you want to share with the group and also present to us as judges. So those are going to occur on Friday. You're going to be held to 5 minutes strict. And tonight you have to sign up with your intention and your group list to participate. And again, those instructions are on the syllabus. It can be a group of 1 or up to 5. We're going to have our instructors as well as a couple of our guest speakers who are going to be judging the final projects, and we have a lot of availability for awesome prizes that you can win as part of that. So please, please, please sign up. Every year, this is a really fun part of the course. If you're registered for credit and you don't want to or can't participate in the proposal competition, you have another option to receive credit, which is a 1-page written report of a recent deep learning or AI paper. So here we ask you, read the deep learning paper, form your opinion and your thoughts about it, and summarize that in this 1-page report and submit it. Again, instructions are on the syllabus, and that too is due Friday. In both cases, the class is graded pass-fail. The competition is only in this sense of receiving prizes for the final project presentations. Tomorrow, we're going to have 2 awesome sets of guest lectures from a couple of our course sponsors. The first is going to be from Douglas Eck, who is a senior director at Google DeepMind, and he has done really, really amazing work in music generation, music recommendation systems, and now leads all of Google DeepMind's generative AI for media team. So overseeing images, audio, music, media in all different forms. And he's super dynamic, super engaging, and I think it will be a really fun lecture. And then that will be immediately followed by a lecture from Comet ML from Nico Lascaris and Douglas Blank. So if you've been going through the software labs, you've hopefully played around with this tool and interface Comet ML, which allows for automatic logging of your machine learning experiments. And they're going to share valuable insights on machine learning in the real world, what skills they feel that, if you're interested in going into ML industry jobs, would be valuable to develop there, and some of the best practices for actually putting deep learning into practice in industry. Again, please attend live to get shirts and listen to these awesome guest speakers. All right, so now let's start with the technical content for this lecture. So far in Introduction to Deep Learning, we've really talked about this idea of how deep learning and AI have been revolutionizing so many different fields, different research areas, from advances in autonomous vehicles and robotics, to biology, medicine, and healthcare, to gameplay and reinforcement learning, and a whole range of other applications in our world today. And so hopefully you've now got an appreciation for not only the areas in which deep learning has made some of these incredible impacts, but also the fundamental workings of these models and the intuition and the math behind how they work. And specifically, we've primarily dealt with two classes of problems in this class. The first, where we are given data, whether that's images, sequence data, data of other modalities, and we seek to make a forward prediction or decision given that data. We've also dealt with what we call inverse problems, where we have some output at the end and we want to try to maybe generate data according to that. And so in both these instances, I think a really powerful framework by which we can think about neural networks is that of function approximators, right? They're learning to try to infer this mapping from data to output or mapping of a probability distribution underlying that data. But in both cases, right, this is a notion of function approximation or probability estimation. And to understand this in a little more detail, I think it really helps to go back to one of the foundational theorems of deep learning and neural networks, which dates back to 1989. And this is this theorem called the universal approximation theorem. And it states quite simply that, let's say you have a neural network. It's a feed-forward, densely connected neural network, and all it consists of is a single hidden layer. You have some continuous function that you want to approximate with this network. What the universal approximation theorem states is that if you have just one layer and you believe that any problem can simply be reduced to input mapping to output via a continuous function, that there exists some neural network that can learn that function to some precision and therefore solve that problem. Now, this may seem at first like a very, very powerful and perhaps surprising result, right? Just one layer, approximate any function mapping input to output within some precision, within some error. But if we look a little further, right, there are a couple of caveats here. The first being that the universal approximation theorem places no restrictions on how large this layer is going to be, right? You could have an infeasibly large number of units of neurons in this layer necessary to get your approximation. Secondly, this theorem makes no guarantees on how well this model actually generalizes. Beyond the range of data that it's seen, what is the performance going to be? And so in this time point of around 1989 and, when neural nets were starting to be theorized and the universal approximation theorem came out, it also puts into context within the broader landscape of the history of AI. We're in this moment right now where we have very, very powerful AI systems that we're going to talk about later in this lecture, and they're broadly useful across many different types of tasks. But that hype, that excitement wasn't always there. In fact, in the history of this field, there have been notable periods where people were very skeptical about the power of neural networks and the power of deep learning. And so I think that helps to contextualize both the current moment that we're in and also the past, right? We're going to be riding these waves of great growth, even exponential growth, but that's always contextualized with times historically where the power of these systems was really called into question. And so that's why in the first part of this lecture, we really want to focus on some of the limitations that come with neural networks and deep learning. Because like any technology, right, it's important to be aware of what those limitations are so that we could best use these systems in practice. And so the first example that I always like to highlight is this notion of generalization. What do we mean when we talk about a neural network's capacity to generalize to new domains and new regimes? So to do that, I'm going to highlight this example from a past paper where they posed this really simple experiment, right? They took images from a large-scale image data set and said, okay, we have some ground truth labels for the classes of these images. But let's say now we take for every image a random die, random chance. And we flip this die, we roll this dice where it has k sides, and k is the total number of possible classes in our data set. And we use this random flip to scramble the labels of our data. So now, the new labels that we've randomly assigned no longer correspond to the truth that's in that image. And we could even have instances where a particular image of the same class, let's say these two images of a dog, are now reassigned new labels that are distinct. So it's complete randomness, complete scrambling of the labels. Now let's say we use this scrambling as a training data set to try to train a neural network model. And the authors of this work did that, and they trained this neural network, tried to fit to a sample of data from this large image data set called ImageNet, ranging from if you took the original ground truth true labels to basically increasing amounts of randomness in the labels all the way to completely random. And as you may expect, right, as you increase the randomness in your labels, on that test set where you really care about the performance of that model, it drops off, the accuracy drops off. But what was really interesting was what they saw when now they looked at the accuracy on the training data. And this is what they saw, that no matter how much you randomize the labels, on the training set, you can eventually fit a neural network that will get very, very high accuracy, close to perfect accuracy. And what this shows and kind of illustrates is this concept that a powerful neural network, as powerful as it may seem, can perfectly fit to completely random training data. And again, this gets at this idea of what is that function approximation operation that the neural network is really learning. All the universal functional approximation theorem states is that neural networks are effectively very good at this task, right? We can always learn a high likelihood estimate of our data such that if we give the model a new data point within the regime of its training data, shown here in purple, right, the neural network is going to produce a maximum likelihood estimate of the output of that function that it's trying to map. So now, okay, this is all well and good, but what if we now spread beyond this regime of the training data, outside those bounds? we don't have guarantees traditionally on how the neural network is going to perform outside this regime. And so this gets at this question of how do we actually understand and calibrate ourselves to the generalization capability of these neural networks? How do we know when a network does not know? And this is a very fundamental question in deep learning that's still very much an open research question and one that we are all thinking quite a lot about. And what is important for you all in practice is that I think with a lot of this hype around deep learning, AI, ML, there's this concept that maybe deep learning is the be-all, end-all cure for all our world's problems, right? Is it alchemy such that, you can have this black box neural network, throw in your data, turn the crank, and spit out some magical solution to your problem, right? But there's this notion that we like to call garbage in, garbage out. Your model is only as good as the data it sees, meaning that if you feed trash in, right, very likely you're going to get trash out. And this is something that, especially as someone for myself, I'm steeped in a very rich and problem-specific domain in biology and medicine. And there's a lot of excitement around these ideas of deep learning and ML, and for me, myself as well. But it always comes back to what is it that we're actually trying to measure? What is it that we're actually trying to represent in these networks? And how good are our data that are suited to addressing those questions? So this kind of idea of generalization, data bounds, uncertainty gets at what is one of the most pertinent failure modes of neural networks today. And so to highlight that, right, let's say we have this black and white image of a dog. We build a wonderful CNN, and we train our model now to color this image in paint or fill in the likely color given this black and white input. And this is what it spits out as a result. And this is a real example. Anyone notice something curious going on with this output? Someone say it a little louder.
Yeah. The
ear is green, yes. What else?
The tongue.
False tongue. The background. Yeah, some things are looking a little bit iffy, right? So let's say now, right, if the model has all seen only images of dogs and trained to colorize, and dogs, happy creatures, right, they're often putting their tongue out, there can be basically biases due to these overrepresentations in the data that end up in the model that we learn as a result. And this is obviously not something that's ideal when it comes to the robustness of a model like this in now doing well and doing reasonably across new instances. And I've shown this example of colorizing images of a dog, but this same concept has much bigger implications potentially. When we think about robustness to these kind of out-of-distribution instances or instances that the model may not have seen before during training. And so very infamously and tragically, some years back, there was this report of a driver that was killed following an accident with an autonomous vehicle operating in autonomous mode. And it had actually turned out that the driver who was killed in this crash had actually reported multiple instances when the car was swiveling into a construction barrier that ended up being the site of the crash. And when they went in and investigated why this actually occurred, it turned out that in the Google Street View images that were used to train the model, there was no presence of this construction barrier that some years later actually showed up, such that the car was passing by in autopilot mode and was swiveling or behaving erratically at this instance that corresponded directly to a point of missingness in the training data. And this is fundamentally driven kind of by this machine learning question that we think about as uncertainty. How do we know when our network does not know? How do we characterize its failure modes? And this is particularly important for what we think about as safety-critical applications of AI, whether that be in autonomous vehicles and driving, in medicine and healthcare, in facial detection systems, and also in general, right, in instances that may not be safety-critical, but still could be characterized by imbalances in data, sparsity in the data, measurement noise from your sensor or from the instrument that you're using to generate your data. And so it's a very, very real problem in terms of how we characterize these notions of uncertainty in neural network models and hopefully mitigate them. A third and final failure mode that is always fun to consider but has very real implications as well is this notion of adversarial examples or adversarial attacks. And the intuition here, and kind of a mind-blowing concept initially, is we can take a data example, let's say it's this image here on the left, and apply a undetectable perturbation of noise such that the result is imperceptibly the same, right, to our eye, the human eye. The image on the right seems basically exactly alike as the image on the left. But when you input both of these into a neural network standard image classifier, the likely class predicted is completely different. And so this small perturbation has fooled that classifier model. And it comes down to how this perturbation is actually constructed and what it's doing, right? So remember that in standard neural network training with backpropagation, our goal is to update the weights of a neural network model using this algorithm gradient descent. The objective is, how does we have some loss function, and the model is performing this operation of making small shifts in its weights to try to decrease the loss and optimize this objective, right? How do we change our weights W to minimize the objective J, or the loss, fixing the data X and the true label Y? Adversarial perturbations, we can construct them by now kind of doing a converse operation, where now we say, how does a small change in the input increase our loss maximally, keeping the weights of the network fixed and the target label fixed? What this allows us to do is now infer what is that difference between the changed input X and the original input X to construct that small perturbation that's effectively seemingly random to our eye, but is actually an adversarially constructed perturbation that can be used to fool the network. And it turns out that you can not only do this with 2D images or other data modalities, but actually create 3D physical objects in the real world that can fool a image classification algorithm. So this is a physically realized object that has been constructed according to information from an adversarial attack and ends up completely fooling these discriminative image-based models. Finally, the final limitation that I'm going to introduce is the concept and the notion of algorithmic bias, right? That neural network models, AI systems more broadly, due to these uncertainties, due to these differences in representation in their training data, can result in significant biases that play out in the real world. And hopefully in exploration of Lab 2 in the course, you were able to get some hands-on experience understanding this in the context of facial detection systems. So these examples that I just highlighted are just three or four out of a long list of limitations and open research questions that we are still thinking about and still working on in the field. And I think that when thinking about these limitations, yes, important to recognize their implications to what models and systems we have today, but also thinking about what opportunities they present from a research perspective, from a development perspective, to actually create new solutions and advances that can address some of these concerns. And so for the remainder of the talk, we're going to transition towards that latter question, thinking about what are the new frontiers that have emerged in recent years that have brought the power of deep learning and AI to a new level, specifically in these capabilities of being very powerful in their ability to encode knowledge in different forms through general purpose learning, and using that to generate new examples, go beyond data, and actually create very, very powerful generative systems. Okay, so for the first part, of this new frontiers portion, we're going to pick back up where we left off yesterday with generative modeling and generative AI. And I think our motivation behind this is really, truly today, we're at an inflection point in terms of the capabilities that we have with these generative systems. And we're going to go further into that in two respects in the remainder of this lecture. So thinking back to yesterday and what we introduced with generative modeling, we talked about two classes of models, VAEs and GANs. And I briefly introduced that these models have a few key limitations, specifically that they can be very unstable to train, right? We chatted about this a little in the context of GANs. They're susceptible to what we call mode collapse, meaning that they get really good at producing the average instance, right, in a data set. And it's very hard to get them to extrapolate beyond the training data that they've seen and generate new out-of-distribution examples. And so these kind of get at some fundamental modeling challenges with respect to the novelty of the generations, the efficiency and stability of training, and really how high quality the generations are. And in recent years, there has been a new modeling framework that is very related to these concepts that has kind of taken the field of generative modeling and generative AI by storm. And that is what we call a class of models that we call diffusion models. And if you are familiar with some of these text-to-image models that you may have played with, like Glide, DALL-E, so on, that are able to take in a text caption and generate an image corresponding to that caption as a result, really the backbone generative architecture behind this is a diffusion model. And so we're going to talk about how diffusion models work, the intuition, the core principles, and also talk a little bit about some of their applications and real-world use cases. So lecture 4, right, we saw about these VAEs and GANs. The unifying component there is that the VAE or GAN performs this one-shot generation step, right? They're taking either random noise or a compression of the data from a latent space and now decoding or generating back out in a single step. The core principle behind a diffusion model is fundamentally different. Rather than doing this one-shot generation, diffusion models are able to generate new samples iteratively by, again, leveraging the power of noise and stochasticity, but instead learning a process that learns to repeatedly remove noise to refine the generation iteratively in a stepwise fashion, and as a result are able to produce very, very high quality generations. And this idea of iteratively denoising or iteratively removing noise is at the core of diffusion models. And to break it down, the diffusion process has two key components. The first is what we call the forward process, or a noising process. And what we do is we take our training data, let's say it's images, and then progressively add noise stepwise, effectively slowly wiping out the details in that data until we have examples of pure random noise. And the important thing to keep in mind here is that this noising process, we can control the function by which we add noise. And we can control how many steps of noise we add, so how long it takes to go from data to random noise at the end. Now, our task is to reverse this noising. These noised examples now form training data for a model that could then learn the reverse process, being able to go from noise to data, gradually denoising stepwise until we get a clean data sample out. So break it down further, right? Underlying this whole process is that forward noising operation, where we're given an image on the left, we sample a random noise pattern according to a function, and then progressively add more and more noise, time step by time step, in this iterative way, such that over these iterative time steps of noising, the result is going to be increasingly more noise. Now, what is really clever here is now we've effectively constructed training examples where we have both our true original image, random noise at the end, and all these iterative steps that are related to each other stepwise by that little residual of noise that was added. Yes, question?
How do we know? Is there a function that defines it as random?
Yes, there is a function that is defined as random, that defines the noising operation. So when you're looking at continuous values, like pixels in an image, standard thing to do is Gaussian noise. With data that's not continuous, like discrete data, let's say it's language, then it is not immediately clear, right? The translation, you can't add a continuous noise like Gaussian noise. So there are other ways to effectively corrupt the data in the discrete case and still perform this same concept of this stepwise corruption and learned uncorruption in that way. Yeah. So now, right, we've basically constructed these iterative examples. Our goal with our neural network model, the backbone model that's going to be the core of our diffusion model, is now asking this simple question of, given an image, a noised image at a particular time, can we learn to estimate the image at the prior time step that had a residual of less noise than what we have currently, right? Given an image at this time, estimate at the prior time step. And this is the objective, this is the task that we're going to try to train a neural network to learn, right? So looking at this example where I have these two images, right? They're differing by just one time step of this noising operation. Any ideas how in practice that we could form a loss function to train a neural network to do this denoising operation? Yes.
Just compare the example again, just find a difference.
Yes, exactly. So your idea was to compare the result at the end of the denoising with what is input. And this is exactly what is done. Initially, what was tried to do was to predict the image all up, right? You could try to learn the pixel values directly. But then it turned out that this is a pretty hard objective. And instead, what's done in practice is comparing those and learning now to predict just that residual of noise that was added. And this is a pretty simple objective that enables stable training of these diffusion models in practice. Yes?
When we do the reverse process, do we know that distribution of the noise function or not?
Great question. So the question is, does the network know the distribution of the noise function? No, right? That's what it's trying to effectively model and learn. So we're asking it, can you learn a probability distribution over this data landscape that will then reflect these stepwise differences? And this is really, really powerful because now you can go in conditioned on a particular time step and basically generate, right, at the prior time step. So it's a very powerful idea. One more question and then I'll continue.
Does the noise mean that, your latent variables are not recognizing structure, and that when you denoise, you have larger values of certain latent variables that correspond to larger structures?
Another great question. So the question is, do we still have a sense of structure with respect to the distribution that is learned? So you can still actually get basically an embedding or an encoding of your data from a diffusion model. So it can function in practice like this kind of latent variable learning. The difference is we're not imposing that strict latent variable lower dimensional bottleneck. It still gives us a mechanism to now get a good encoding of the data, but it's a different setup in that our task is to basically model this residual difference as a way of learning the structure in the data. All right, so this tells us this reverse process is how you actually learn the weights of the backbone neural network architecture in a diffusion model. Now, when it comes time to now generate a new sample, a brand new data instance, what is done is you take your trained neural network diffusion model and then start with complete random noise at the beginning and perform this stepwise decoding operation to iteratively generate these samples step by step, repeating the process over this denoising operation such that eventually you can reconstruct and generate a new sample. I kind of misspoke there when I said the word reconstruct, right? Because this is slightly different. And you may be asking, okay, well, if I start with let's say I start with the same set of random noise and I run it twice through the model, will I get different generations out? And the beauty of diffusion is that the answer is yes, you can, because you have stochasticity in each of these operations, right? The neural network is learning this inverse process, this reverse process, such that you can generate the new samples stepwise and then result in new generations at the end. So putting it all together, right, with diffusion models trained to predict and infer this denoising process, and then we can sample brand new generations by taking the trained model and performing the iterative denoising to start back in the data space. And so the real power of this approach comes from this fact that in starting from random noise, you have maximum variability, right? But by learning that residual stepwise process, you're making the task more stable, more digestible for the model to learn. And as a result, you can get very, very high fidelity and high quality generations starting from something that captures a high degree of variability. And what's really striking, again, as I kind of alluded to, is that different instances of noise will produce very different generations as the end result. And indeed, right, as we introduced in lecture 1, the diffusion models are what underlie many of these text-to-image generation models that are out there, right? And the ability of these models allows us to actually take representations from data like language and use that to condition or guide the diffusion models' generations to now produce instances based on these prompts. And you've probably seen many examples of this. Here I'm highlighting just a few. So far, we've really talked about images as kind of this example use case to get our heads around the intuition behind these models and how they work. What about other modalities or applications? And to me, I'm very biased here, but one of the most exciting spaces to think about the power of these generative models is in biology and chemistry and in molecular design. And in recent years, we've really found that diffusion in particular is an especially powerful framework for this. And so people have shown very promising results in now thinking about not pixels in 2D or 3D spaces, but the coordinates of atoms in space. And designing diffusion models that are very similar in concept, but can now create instances of these position-wise coordinates to create new molecular entities. And in some of my own research over the past couple of years, we've really focused on developing new diffusion modeling frameworks for questions in biology and in protein design in particular, where the motivation here is that we are seeking to design new biomolecules like proteins that can expand our therapeutic capabilities, our chemical capabilities, our functional capabilities. And to give you a very brief primer on the concept here, proteins, right, they're kind of the actuators of all of biology. And they're encoded by a sequence of these chemical building blocks that we call amino acids. And the paradigm is that that sequence, that language of amino acids, dictates a protein's three-dimensional structure, and that dictates its function. And so what we've done is we've developed new diffusion-based models that can generate new protein structures. So thinking about, let's say, the set of angles that would represent a protein's configuration in 3D space. You can think about the random state as a completely unstructured, unfolded state of the protein. And we can actually build a diffusion model that looks at these data and has learned to now generate structured sets of angles that correspond to a backbone of a protein in 3D. And so this example that I'm showing in this video here is a visualization of that denoising process over time, where the model is making these iterative refinements to produce a backbone structure of a protein. Beyond this, right, we can think not only of structures in 3D, but how we can actually expand this to now think about much, much larger scale data sets that are on the scale of all of evolution. So we've extended this idea to now not think about continuous values, but treating protein sequences as a language, where we can take a data set of over 50 million unique protein sequences from many, many different organisms, many different functions all across the tree of life, and build a generative model that can learn to generate new protein sequence instances such that we can create over this language of biology and now realize new sequences that hopefully have strong functional capabilities in the real world. And indeed, it's not just myself and my colleagues and teammates that are thinking about this. This is really a huge wave in biology right now, where we've now arrived at the point where some of these AI-generated protein designs have been validated experimentally and starting to think about therapeutic applications and use cases, like in designing binders to the COVID spike protein, for example, that could, in theory, be deployed in a therapeutic context. So, all to say, this is a tremendously exciting time for generative models and their intersection with different fields. So in the final portion of this lecture, and to close out this course, we have a new set of content on, I think, what hopefully is a very exciting and pertinent topic, and that's large language models, which are a class of models that have kind of taken the world by storm over the past year. And indeed, right, I think we posed this question earlier, but pretty much all of us have interacted with models and tools like ChatGPT that allow us to now interact with these very powerful AI systems through natural language as our interface. And so in the remaining portion of this talk and this lecture, I really want to break down, this question of what are large language models, or LLMs? How do they work? What are they good at? What are some of their limitations? And where do we go from here? So very simply, at the highest level, large language models are a class of neural networks that are very, very, very large, meaning that they have extraordinarily high numbers of parameters and sets of weights, and they're trained on very, very, very large data sets. And it's this combination of huge data, huge size and scale that has kind of given rise to these powerful capabilities of these models. And so a model, an LLM like GPT or ChatGPT, fundamentally, how does it work? What is so mind-blowing about these models is that the way that they're built, that the way that they're trained is a very intuitive concept. And it's one, in fact, that we've already introduced and you've seen in this lecture back on day one. And the concept here is that you take a big general purpose data set, unannotated, large amounts of text from the internet, from other sources, so on. You take that text, you split it up into chunks, what we call tokens. It's not necessary that a token is a word. Oftentimes a token is a word, but there are different clever ways to do that chunking that's shown to be maximally good for these types of models. You then have a model. It's very large, on the order of hundreds of billions or even more parameters, meaning distinct weights. And the backbone of these models is very dominantly a transformer architecture, right? Where we talked about on day one of the class. How do you actually train this model? A model like GPT is trained on a pretty beautiful task and an objective, which is the following. Given a sequence of these token chunks, predict the next token. And we're going to update the model's parameters, its weights, based on how good it does at that next token prediction task. And if you recall back to day one, lecture 2, right, this is the next word, very similar to that next word prediction task I talked about in the sequence model lecture. And so, breaking it down stepwise, how fundamentally does this next token prediction task work? LLMs like GPT, right, you start with your text data, it's raw text. The first step is this chunking procedure, what we call tokenization. And oftentimes those tokens are converted to an embedding, right? Again, a concept from day one, converting text into this numerical representation in a way that we can pass into our neural network. The large language model now sees these tokens, and it's going to see them and be asked, given a set of tokens, what is the likely next token, right? And so you can think about this in a context that we're effectively shifting the prediction over by this window of 1. So let's say, and you can see that visualized here, right, where the predictions of the next tokens are shifted by 1 relative to the individual tokens in this input example. What the large language model then generates is the format of the predictions is a distribution of probabilities over all possible tokens in its vocabulary. Meaning, what are the likely next tokens that are predicted, and what are the scores, the probability scores, across that set of tokens. And in practice, right, we can use a function like a softmax, which enforces us to produce values between 0 and 1, such that we're guaranteed we have a probability distribution over these tokens. Now, to evaluate how good this prediction task is, all we have to do is compare via a pretty simple loss like a cross-entropy loss across that predicted probability distribution versus the true next token. And that's it, right? This is so elegant, right? This principle of next token prediction. But the beauty is that by combining these very large-scale data sets with this objective, our idea is that the model is going to learn a pretty good representation of the world if it sees these text data from all different sources, all different facets of human-created content, right? Then, once you have your trained model in hand, you can use it at deployment, at inference, to now generate new text instances based on what we call a prompt or an input. And again, the backbone that's running this is, again, that same next token prediction task that's actually being used to generate text when you interact with something like ChatGPT. And so the capabilities that are feasible right here and right now with these large language models are truly significant in their ability to manipulate and master natural language, to do things like knowledge retrieval, to write and create new content, to guide planning through this interface of natural language. And yet, that being said, right, there are key limitations that still exist with these LLMs and what they're not so good at today, right? Oftentimes, they produce nonsensical generations. And so we still have that question of how robust is that model? How can it confer to us when a generation is good and confident or when a generation is more uncertain? It may produce generations in which it's confidently wrong or that are completely ungrounded or nonsensical or what are often called hallucinations. Can we detect these reliably to refine our interaction with the model in that way? Furthermore, right, there's this big question of, with a powerful system like this, how can humans be trusted and instructed to set up reasonable guardrails against these models to mitigate against potential adversarial attacks or adversarial jailbreaks that could derail the model and send it off the rails, right? And finally, in terms of some of the fundamental kind of numerical or mathematical capabilities with respect to logic, these models still demonstrate some key shortcomings. And so kind of the theme here is that this high-level thinking process is still, at its nascency in terms of how these models are able to generalize and perform in this way. But one thing we do know is that there are interesting and curious things that happen as these models get larger and as the data sets that they're trained on get larger. And this gets at this notion of emergence, meaning a property or an ability of these large language models that's present as you scale bigger and bigger, but not present in something that's smaller. And it turns out that you can describe this precisely and mathematically by what we call scaling laws, where people have charted out a relationship between the size of the model, how many parameters it has, and how good it performs on kind of cognitive types of tasks. And so there's this question of, is scale going to be all we need? Is it true that, we can scale these models to a very large point such that the capabilities become greater and greater? And people have already started to kind of chart this out with this notion of emergence and made observations that as you scale the parameter count and the size of these models, the capacities do seem to increase. So all told, right, we're kind of getting at this very powerful idea, this notion of what is a foundational model or a foundation AI system. And broadly, what we mean by that is a model that can be trained on these unannotated, large, general data sets, but can be adapted and perform well and robustly on a wide range of tasks. So beyond this paradigm of a classifier model for classification, a regression model for regression, can we arrive at more general purpose systems that can function more as reasoning engines? And this starts to get at really big questions, right? How can we interface with these models and these AI systems most effectively to use them as tools that work alongside us, alongside our own creative process to help tackle different problems, different questions that our society faces? And so with that, I'll leave you with that thought and things to ponder on. It has been a pleasure to talk about this, and we're all very open and curious about these questions. I know I am, I hope you are, and looking forward to continuing the conversations in the remaining hour and also throughout the next couple days. Thank you.